This video shows the chapter 7 slides, which are about indicator variables, in other words, dummy variables. A dummy variable is used when you have categorical data and like gender, which is male or female, or drink preferences, Pepsi versus Coke versus Sprite, those kinds of things that are categorical, but you want to classify them in terms that can actually be quantified so that you can run a regression. So when we generally think of a dummy variable or indicator variable, we think of one that has two choices. So we'll call this D, and it usually takes the value of 1 if the characteristic is present and 0 if the characteristic is not present. So adding the indicator causes a parallel shift in the relationship between the independent and dependent variables by the amount of the coefficient on the dummy variable. In other words, it captures a shift in the intercept as a result of some quantitative factor characterized by that dummy variable. So you'll see this, an example of a dummy variable would be, to classify gender would be male. So male would take the value of 1 when the subject is male and 0 if the subject is female. That's one we'll see. So in this example here, we're showing how the use of the dummy variable will cause the intercept, the y-intercept, to change based on whether or not an individual falls within that group or not. So there's two choices. D can take a value of 0 or 1. We're going to call 0 the reference group or base group. So for a male versus female dummy variable, if we call that males and say male is 1, then the reference group would be females, in which case the dummy variable would be 0 in that case. So here what we see, beta 2, the coefficient on the dummy, captures the change in intercepts. It allows us to determine whether or not there is a change in the y value based on the group. So based on, in our soon-to-be example, gender. In other words, it adjusts the change in your average y. So the change in average y is captured by that change in intercept, which is your beta 2 characteristic. We can use t-test to determine whether or not this intercept is going to be statistically significant. So let's go through here. Is the coefficient on the dummy variable statistically significant? Well, just to know that, you're just testing HO beta of the dummy is equal to 0, and Excel default gives you that, so all you have to do is look at the p-value of the t-statistic on the ANOVA table. Now, you can only do that when you're looking at an indicator or dummy variable of only two choices, so be careful. If we have more than two choices, you won't be able to just look at that p-value anymore, and we'll discuss that later in these slides. So what would that tell you? Well, that would tell you whether or not that characteristic being present changes your y value or changes your dependent variable, meaning does it have an impact on your dependent variable. But that wouldn't tell you whether or not that impact was positive or negative. In order to conclude that, you would have to do your hypothesis test, and you'd set up your standard hypothesis testing table in order to evaluate that. Hold on, why are we not going to the next slide? Okay, so let's look at an example. This example is Harris 7. It contains education or data on the years of education for a bunch of employees at this Harris company, I guess. The number of months of experience, the number of months that they've been with the firm, and then this dummy variable, males, which takes a value of 1 if the subject is male and 0 if the subject is female. So I can look here and I see the coefficient on males is 722.46. This tells me that on average, men make $722.46 more per month, our dependent variable here was salary, than do females. So male is the characteristic being present when that is 1. My reference group is females, in which case the characteristic is not present, in which case male is equal to 0. So this when that characteristic is present, it tells me the change in my dependent variable as a result of that characteristic relative to my reference group. So that's why I'm saying that males make on average $722.46 more than do females. I can look at that p-value there, and my p-value is less than 0.05, so I'm 95% confident that males make, on average, $722.46 more than females, ceteris paribus, or holding education, experience, and number of months with the firm constant. Now to test... so is the coefficient on the dummy variable statistically significant? Yes, and I show the printout here also in SPSS. But in order to determine whether or not males have statistically significantly higher salaries, I would have to go through and conduct a specific hypothesis test. So I went through and did that here just to see whether there's a positive, whether gender, male, has a positive impact on salary. I'm just testing relative to a hypothesized value of 0. So HO would be beta males is less than or equal to 0. So I'm going to look at my p-value lower. That's definitely less than 0.05. So I would reject HO and conclude that, yes, males in general do make statistically significantly more than females. And this is also characterized by the fact that, I'm looking in my 95% confidence interval up there, and there's no negative range in there. So it's pretty much impossible looking at my confidence interval to say that males don't make more. I could do that same hypothesis test looking at my printout from SPSS, because I want to know, does being male have a positive impact? And T is positive, so all I have to do is take my significance, which is my p-value, and divide by 2. 0 divided by 2 is obviously still 0, so again, I would reject HO and conclude that men do make statistically significantly more. Okay, now what if you have more than 2 choices? If this happens, you have to pick something called a base category and then create one indicator variable for each category. In general, if there are m categories, then you will use m minus 1 indicator variables in your regression. If you don't do that, you fall into what's called the dummy variable trap, and you introduce perfect or exact collinearity. Remember, what are you doing when you have this dummy variable? You're causing the intercept to change. Well, before we only had 2 choices, 0 or 1, and if the characteristic was present, then your intercept would increase. If it wasn't present, it wouldn't change. Now, we're going to have more than 2 choices. So let's say you had 3 choices. If you created dummy variables or indicator variables for each of those 3 choices, then there would always be a situation where one of those was a hit. In other words, one of those 3 categories was present, in which case you would always cause your intercept to increase, therefore therefore always causing that value to be 1, and therefore you really wouldn't be able to see the impact in each individual category. The fact that you would always cause that to increase is introducing that perfect collinearity, because you're always causing that impact to be 1, since you will always have 1 hit. But the reason you really care about that is the fact that if you do that, you won't be able to see the impact of each category, which is really what you're concerned with and why you're bothering to make these dummy variables in the first place. So how do we do this? Coding for multiple indicator variables in Excel, you're going to use the if function. In SPSS, you're going to go through and transform and use your transform function to create a new variable, and you're going to recode into different variables. And you can look at the video that shows you exactly how to do that. So now we have more than 2 choices. So we can't just look at our t-statistic anymore to determine whether or not our dummy variable is statistically significant. Instead, we'll have to do a partial F test. So you will classify your full model, the ones that are subscript F, as the model with all of the indicator variables. Now I'm saying all, but it's actually 1 minus the total number of categories that you're going to consider. And your reduced model would be your model without any of the indicator variables. And then your HO would be the indicator variables do not add to my regression or are not statistically significant. All of their betas are equal to 0. And your HA would be that, they do add value to your regression. All of their coefficients are not equal to 0. So you'd reject HO if the F that you get is greater than some F comparison, this F critical value, which is found using the F inverse function. And just remember, when using this, N is the number of observations that you have in your model, K is the number of independent variables in your full model, and L is the number of independent variables in your reduced model. The way to remember that, L must always be less than K, so L for less, L has to be the smaller number, and then N is just number of observations. Okay, so here's an example. We have this company, Metacorp, and they work in 3 regions, the South, the West, and the Midwest. And we're looking at the sales in 25 categories based on the advertising expenditure in that, sales in 25 territories based on the average expenditure in that territory and the bonuses paid in that territory. So those territories, those 25 territories are over 3 regions, South, West, and Midwest. We have 3 choices, but we can only introduce 2 indicator variables. Otherwise, we'll introduce perfect multicollinearity and we won't be able to see the impact of each of those territories. So I'm going to, here's showing how to code the variables in Excel using the if functions. You'll see the output for coding this in SPSS. And what I'm going to do, I have region, which is the data that comes up, and it's always region 1, 2, or 3 based on where they are. And I'm going to create now 3 new indicator variables based on that region. So if region is 1, then they are in the South, so my new dummy variable South would take a value of 1. If region is 2, meaning they're in the West, then my dummy variable South would take a value of 0, because they're not in the South, they're in the West. If region is 3, that means they're in the Midwest, so my dummy variable South would also take a value of 0, because they're not in the South, they're in the Midwest. The same goes for West. It only takes, the dummy variable West only takes a value of 1 when they were in region 2, which is the West. The dummy variable Midwest only takes a value of 1 when they were in the Midwest. It takes the values of 0 otherwise. But when I go to run my regression, I have 3 dummy variables. I can't include all 3 of them. I have to select one of them to be my base or reference group. So I'm going to select Midwest to be my reference group. So we go through here, and I ran the regression, and you can see the output in Excel in orange and then in SPSS in white, and you're going to get all the same results. So the regression equation is sales is equal to 435 plus 1.37 advertising plus 0.975 bonus minus 258 South minus 210 West. So if you are in the Midwest, if you are in our reference category, then South, the dummy variables South and West, both have values of 0. So your equation is just sales equals 435 plus 1.37 advertising plus 0.975 bonus. If, however, you are in the south, then your dummy variable south takes a value of 1. Well, if your dummy variable south takes a value of 1 and your variable west takes a value of 0, then negative 258 times 1, well, then you're just ending up with a number, right? So you would have two numbers in here, and I can reduce this, and that's why you see the that's why you see the intercept, or the amount of sales when advertising and bonus are equal to 0, actually changing for that southern region, because I'm taking that 435 and subtracting off the 258 that we get if we are in the southern region. So you will see the intercept actually change based on whether each of those dummy variables has a hit. So same way, if we're in the west, south would take a value of 0, but west would take a value of 1. So my intercept of 435 would reduce by 210. So in the west, sales would be equal to 225 plus 1.37 advertising plus 0.95 bonus. The rest of your interpretations would all go in the same way. But I still need to know, are my dummy variables statistically significant? So in order to do that, I'll have to conduct my partial F test. So HO would be my dummy variables are not statistically significant, meaning that region has no impact on sales. And I will calculate my SSEs from my full and reduced model here. And my F compare is 17. My F critical is 3.5. So my F compare is definitely greater than my F critical. So I would reject HO and conclude that that region does have a statistically significant impact on sales. The next thing we're going to look at is seasonal effects and time series data. Time series data is where you're looking at one specific observation repeatedly over a long period of time. So usually we think about this as sales. Another example, sales per day, sales per week, sales per month, sales per quarter, something like that. Another thing you could think of would be temperature, or I don't know, anything that you can observe repeatedly over a long period of time. Weight would be another example. Now, if we want to determine if there's seasonal effects, we might think that the dependent variable depends on the calendar, the season, the time of year, day, month, quarter, something like that. And we can do a seasonal adjustment by adding dummies for the relevant time period as independent variables. So here are the steps in here, and for this I kind of recommend that you do a mix of SPSS and Excel. Your first step is going to be to create a trend column. This will just be 1, 2, 3, 4, 5, just literally indicating, that your data is in some kind of order. The next will be to create a seasonal effect column. So if the data is quarterly and you're analyzing quarterly effects, then create a series of 4 quarters and repeat that over and over again, versus if your data is monthly, you would create, a column called months, and you would, 1 through 12, so on and so forth. I highly suggest that you do that step in Excel, because you would need an add-on in SPSS to do that, which means you have to fork over some money, which is not so nice. I do not believe we have that add-on for us. I haven't been able to locate it. So do that part in Excel, and then you can upload that data to SPSS if you'd like to run SPSS. You could also go through and create the individual dummy variables for your quarters, months, seasons, whatever, in Excel, or do them in SPSS. That's 6 of one, half dozen of another. Not that big of a difference which program you use. Then go through and run your regression. Again, in either program, not that big of a deal, but where you want to use SPSS is to check for autocorrelation. It is possible to do the Durbin-Watson test in Excel, and I'll show you on the next slide where I actually performed that in Excel, and you can look at the values there. But it's a lot of calculations versus in SPSS, you click the little button that says Durbin-Watson test. Now remember, for the Durbin-Watson test, this isn't something I can just look at a p-value. I actually have to look up the DL and DU in the critical values tables. So remember, you'll have your Durbin-Watson table available to you. I have it posted. It's also in the back of your book. You'll have access to them for exams and homework and stuff like that. So then check for this. So after you've checked for autocorrelation, well, what happens if you fail your Durbin-Watson test and you do discover that, you have autocorrelation present? Your solution will be to add a lagged observation into your data set to actually make that correction. So if you're using sales, add lagged sales as a dependent variable if you discover that you have first order autocorrelation. Then perform a partial F test to test whether or not there really was a seasonal change, and you're going to have to remember to do that on your corrected model. So if you failed the DW test, you need to go through and make that correction before you do your F test, and then you can use the model to make any predictions. Oh, sorry, bring that back up for you. Okay, so here I went through, this is, showing the DW test for data on ABX sales. And here our Durbin-Watson statistic is 1.84, the DL is 1.29, and the DU is 1.72. So we do not reject HO. Autocorrelation does exist, so I will need to make a correction. And you can see when I go to run my model, the one that I'm going to be using, I have my trend variable, but then I also included lagged sales. So my value of lagged sales is the value of my previous sales. So obviously when I run this, when I run the corrected model, there's one less number of total observations that's included in there. And here I was doing this for quarterly data, so you will notice obviously there's 4 quarters in the year, and I only ran it with 3 quarters of dummy variables included. Quarter 4 would just be my reference quarter, so my equation for sales in quarter 4 would be 198.48 plus 2.41 trend plus 0.067 lagged sales. Okay. So how would I use that in predictive purposes? Do I have a seasonal trend? Yes, I did my my F compare, and I do see that the full model is in fact better. Now, how would I use this? What is my lagged sales? How is this going to go on and work? So let's say I want to predict the first quarter sales in 2004, and my data ended with quarter 4 sales in 2003. So if I look back here, I'd start out sales equals 198.48 plus 2.41 trend. So whatever my last trend variable or trend observation was, let's say I had 50 observations, then trend would be 51 for my next observation, right? Okay. Plus 0.067 times lagged sales. So look at the previous sales value and include that in there. Then I'm trying to predict quarter 1 in 2004, so plus 1.59. And that's how I'm going to get that quarter 1 sales in 2004. The next example looks at interaction terms. So here we're looking at a model that now has 2 independent variables. One regular normal independent variable, and one dummy variable. So the 2 x variables here as independent variables are actually x1 and d1. So if you're looking for an x2, you're going, what's going on here? Okay. So one regular independent variable and one dummy variable. Now what I'm going to do here with this interaction term is I'm literally going to create a new term, which is going to be my interaction. And that is going to just take, I take my first independent variable and I multiply it times my dummy variable. And when I have this interaction term, I actually cause the slope of the line to change. So each dummy variable yields a different slope in the relationship between between my dependent variable and x1. So what I'm doing here really, I'm showing that the slope changes based on the group that I'm seeing in my dummy variable. So if groups are gender, male or female, I'm showing the change in whatever my x1 is, let's say age, change in age associated with gender. That's what my interaction term will allow me to do. And we can see that here. If my dummy variable takes a value of 0, then my interaction term is not triggered. There will be no change in my intercept, and there will be no change in my slope. But if my dummy variable equals 1, meaning my dummy variable is triggered, there will be a change in both my intercept, characterized by beta 0 plus beta 2, and my slope, which is now characterized by beta 1 plus beta 3. So when I have that interaction term, not only does my intercept change, but the slope of my line also changes. So what this does is it takes the average change in your dependent variable and shows how that change is different for each of the different groups. Okay, so let's show this graphically. Hold on. Okay, in our first graph here, the slope of the line is red, and that's the coefficient on beta 1, which is the coefficient on your x variable. Let's say age. If the dummy variable is present, then this slope will, or this intercept will increase by beta 2. So blue, which is our new slope, which is our coefficient on our dummy variable. Then when I include an interaction term, not only does my intercept change, but my slope changes too. So my second graph, my red line is still my slope, my coefficient on my x variable. If there's no interaction term and d takes a value of 1, then my intercept just increases by the coefficient of my dummy. So it would just go to that blue dotted line. But if there is an interaction term, then it changes to the blue solid line because the slope itself actually changes by the coefficient on that dummy. So beta 0 plus beta 2. I'm sorry, beta 0 plus beta 3, which is that coefficient on that dummy variable. So in our example here, what we're going to do is look at the data set Harris 7. It gives us information on education, experience in months, the number of months the employee has been with the firm, and a dummy variable males, which is 1 for male and 0 for female. So again, this is what we've looked at before, and our dependent variable is salary, which is monthly salary, and we want to create an interaction term, education times male. So what this will actually show us is how does gender impact education, or how do gender and education together impact salary? Meaning, it'll allow us to test, do males with more education make more money? Because it will allow, or it will cause the slope of males to change based on the amount of education, or the slope term on education to change based on gender. So it's going to show you the interaction of those two. So instead of just looking at the coefficient and saying, yes, I know that male is 1, and female is 0, so males are my reference group, I know that males make more money, I think we also had a positive coefficient on education, so I know that, you know, the more education you have, the more money you make. Now I want to know, is there a specific impact? Do males with more education make more money than females with that same amount of education? Meaning, is the slope of that relationship actually changing? Is education more beneficial for a male employee than it is for a female employee? So here I have my printouts in both Excel and SPSS. And I'll need to conduct a partial F test in order to see whether or not the new coefficients, males, and the interaction term are in fact statistically significant, because now, in effect, I have more than two choices in here. I have more than one dummy variable and hence more than two choices. So on the next slide, I actually do discuss, I believe I show you, or in the printout you can see in the example video, I do perform a partial F test there, and we do see that even though these p-values don't look statistically significant, our partial F test does reveal to us that they are statistically significant. So what's interesting here is it looks like the coefficient on males turned negative here, which makes it look like being male actually causes your salary to decrease. But that is not true. I'll go through in class, we'll do an example where we'll actually plug numbers in, and you'll see that once we take this interaction term into account, for each additional year of education, a male's salary will increase by roughly $82 per month. So the impact of gender now is not negative, because that impact is being split between the regular gender variable and the amount of education. So here what we're seeing is that, you can do that interpretation there. And we have that same printout in SPSS as well as Excel, and you see you do get the exact same results. Which independent variables have a statistically significant impact on salary? Well, if I look back here, yes, I can just look at the p-values on education, experience, and months, and those are all statistically significant. But to evaluate the impact of gender, I now have to perform my partial F test in order to see whether or not that is statistically significant. And the reason behind that is, think of before when you had more than two choices, right? What you did was actually create additional dummy variables. So anytime you have more than one dummy variable that you're running in your regression, you really do need to do that partial F test instead of just looking at the p-values in order to determine statistical significance. Okay, go down. Come on. Respond. Okay. Okay. And then is there any statistically significant difference between the salaries of men and women? Yes. We do find that for each additional year of education, men make statistically significantly more, specifically $81 per month more.